Good evening and welcome to the Orkney International Science Festival online. My name is Heather Woodbridge.
And my name is Kathy Hunter.
This evening's event takes place at a time when climate change is coming further to the fore and questions are being raised about the amount of fossil fuel used for aviation and shipping.
But an island community needs its planes and ships, and pioneering new projects are underway to look for possible solutions. We have new developments here in Orkney to do just that, and our speakers here this evening are going to tell us more. To introduce them, we're joined by Noor van Veldsen, Hydrogen Project Manager at the European Marine Energy Centre, or EMEC for short, which is based here in Orkney. Noor is a civil engineer from Delft in the Netherlands who came to Scotland to work in marine renewables at the University of Edinburgh. So over to you, Noor.
Thank you, Heather and Katie. So our first speaker tonight will discuss some of the pioneering aviation activities and developments at the Kirkwall airport that have been in the news recently. So that in the news was with the flights of the hybrid electric aircraft. And that aircraft was developed by the company Ampaire, whose chief engineer is Andrew Rae. He worked in industry for more than 20 years and in 2010 moved to academia and is professor of engineering at the University of Highlands and Islands. And just before I start, I should also say that if you have any questions, please enter them in the YouTube live chats. There will be then an opportunity to come back to them at the end of the presentations. We hope you enjoy the talks. Andrew, over to you.
Thank you very much, Noor. It's a privilege and a pleasure to be here tonight and explain to you some of the work we've been doing recently, which some of you may have seen in the news, around Ampaire's aircraft flying from Wick to Kirkwall, which is part of the Future Flight Challenge, which is the UK government part-funded programme being led by Highlands and Islands Airports, looking at the infrastructure and the platforms necessary to achieve lower carbon aviation. So that's me. That's the title of my talk. So next slide, please. So I wanted to describe a bit of the journey that Ampaire have been on to arrive at the flying demonstration that we did recently in Orkney. So the aircraft we use is a Cessna 337, which was chosen because it's a twin-engined aircraft, but has both engines in the fuselage. So it has twin-engine safety and reliability, but also if one engine fails, you don't have any asymmetry in thrust, which can cause a problem for flying control. So in this iteration, the front engine has been replaced by an electric motor, and it follows on from a previous version which had the rear engine replaced. So next slide, please. So this is the first iteration with the rear engine replaced by an electric motor. So you can see there the layout, the silver plate on the right-hand side is the rear bulkhead. So we've taken the internal combustion engine out and replaced it with an electric motor and an inverter and cooling for the inverter. And then there are the systems that go around that, so that the battery management system and the power plant system as well. Next slide, please. So the version that flew recently in Orkney, as I said, had the front engine replaced with electric motor. So the bottom right-hand side there, you can see some of my colleagues at Ampaire, and the picture above that is where the internal combustion engine used to be, and now there's quite a large void showing where the silver box with the blue cable going into it is the inverter. The black donut at the front is the motor, and the rest of it then is to do with cooling. And because this part of the aircraft is near the nose, and because the motor weighs a lot less than the internal combustion engine, we've had to put ballast in there to keep the weight and the balance the same. And the battery sits in a gondola underneath the fuselage. Next slide, please. So the original aircraft was built in 1976, and so we took the decision to replace the front engine. And on the right-hand side picture there, you can see just about maybe in front of the right-hand yoke is what looks like an iPad with some green lines on it. That's the new electric motor management system. So it gives us things like the current state of the battery, the motor temperatures, and that sort of thing. So it's the things that the pilot needs to know about for the alternative power plant. Next slide, please. So we went through a development process, and I'll describe each of the black boxes on the right-hand side in more detail in a minute. So the original incarnation with the rear engine went through a successful flight demonstration, but that followed a series of component level testing and feasibility tests for the configuration that we'd chosen. And before it flew, we did some taxi tests just to make sure that the aircraft was functioning correctly. Next slide, please. So the first phase of that is what we call a copper bird. So the copper being electrical wire, it's testing the electrical system off the aircraft. So we have a caged motor and propeller there for safety on the left-hand side. And all of the electronics and control systems needed to control that motor were tested on a bench before it ever went anywhere near an aircraft. And it's important also because there's quite a bit of software involved. We can test the software fully without endangering any aircraft. Next slide, please. So then we move from the copper bird to the iron bird, which was the same airframe, but an old expired airframe that we then installed the system into to make sure that everything integrated into the aircraft. So we did that for both the replacement of the rear engine and the front engine. So it's checking the installation, checking that we can fit everything where we need to, that the wiring and the cabling works, that the software works in situ in a representative airframe. Next slide, please. So as I said, we had to test all of the software, and that includes the motor control, which the pilot has the main input to, but also the battery management system. So one of the problems with batteries is thermal effects. So we don't want thermal runaway. You've probably all seen what happens when lithium-ion batteries get too hot. But also we needed, as part of the safety case for the aircraft, we can discharge the battery at a greater rate than normal, which gives us 5 minutes of full power on the front engine. So for example, if the rear engine failed, it gives us an opportunity to land the aircraft safely at a point of our choosing rather than just where the aircraft decides to fall. Next slide, please. So a lot of the work is also what's called the human machine interface. So it's understanding what information the pilot needed to monitor the aircraft, as well as all of the scientific data logging that gives us an idea of the performance of the battery and the motor, not all of which is needed by the pilot. So it's refining which parameters the pilot needed to see, presenting those in a manner that was easily readable, and so that we could then go to flight testing and the pilot had confidence that he was in control and had enough information to determine the state of the aircraft. Next slide, please. So the bottom right-hand picture there, the silver box is the battery pack. It's fixed to the bottom of the fuselage through some load points, which on a traditional Cessna 337 are used for a baggage gondola. And you can see on the top right-hand picture there how little of that original engine space is taken up by the electric motor and the inverter. So obviously we've got the weight of the battery, but where the motor sits, there's a vast gap, which if we were designing a clean sheet, we could optimize to reduce the volume of the motor. And we use a company called Wasabi Flight Test, who a couple of guys in the US who have done a lot of civil flight testing experience on lots of different types of aircraft, who understand the importance of safety and the science in the development of an experimental aircraft. Next slide, please. So once we'd done all the Ironbird, we created the aircraft that did its first flights in California. and it did 24 flights over a period of 28 days, accumulating just over 33 flight hours, and nothing went wrong with it. So we had 100% dispatch reliability. It has to be said that the electric motor is much simpler than an internal combustion engine, obviously. So the maintenance and reliability is much improved. And at that point, we recorded the longest electric flight, which was 341 miles, lasting 2.5 hours. And we broke that recently, and I'll come to that later. So next slide, please. So having successfully flown in California, the aircraft was taken to Hawaii for flight testing on some airline routes there. And again, we did over 20 flights over a period of 17 days and accumulated more than 20 hours. And again, nothing went wrong. So this was the first trial of a hybrid electric aircraft on actual airline routes within Hawaii. Next slide, please. So there's some interesting scenery in Hawaii. So there's a part of a volcano there, and flying over water in an electric aircraft is one of the safety cases that we have to address. And obviously we had to do that when flying from Wick to Kirkwall as well. So next slide, please. So the aircraft was shipped from the US to Grangemouth, arriving there on the 17th of July. It arrived at Wick by road in a shipping container on the 20th, and NHV helicopters at Wick kindly donated space in a hangar for us to reassemble the aircraft. We did some check flights on the 4th of August, and then it made its first flight from Wick to Kirkwall on Friday the 6th of August. So that was the first flight of electric aircraft, hybrid electric aircraft in the UK. So top left is the aircraft doing its first arriving in Kirkwall, and then there's a nice picture from the control tower at Kirkwall taken by one of the air traffic controllers of its first departure on that Friday. Next slide, please. We had a wonderful launch event the following Thursday, which was attended by Graham Day with the Scottish Government Minister. We had planned to do around 7 return flights, but the weather curtailed that. The aircraft has to fly in what's called visual flight rules, so we're not allowed to fly in cloud or in visible moisture, such as rain. But we did do, I think, 4 return flights between Wick and Kirkwall. And on the right-hand side, there is a picture of Kirkwall Airport from the aircraft on the Sunday, where it did flew over to Kirkwall but didn't land. Next slide, please. So Ampaire is part of 2 programs within Future Flight in the UK, and the other one is based down from flying between Exeter and Newquay and then to Land's End. So we broke our own record the following Monday when the aircraft flew from Perth, where it had to land to replace a faulty transponder, flying 418 nautical miles from Perth to Exeter, which is our new record. And then it flew from Exeter via Newquay to Land's End. So we've done Land's End to John O'Groats, and on the right-hand side there is a photo of the aircraft at Land's End and coming back to Exeter, which is a flight I was very privileged to sit in on. So next slide, please. That's it for me. So thank you again very much for the opportunity to talk to you about Ampaire's participation in the SATE project, and I'll hand back to Noor.
Thank you, Andrew. Then also at the Kirkwall Airport, a new project is underway to use an unmanned aircraft or drones for cargo delivery. And this is led by Herman Moreno, who is the head of flight operations at Windracers, an organization established to use drones for work for public benefit. Herman, the screen is yours.
Thank you very much, Noor, for the introduction, and thank you for the invitation to the event. So my name is Herman Moreno, and I'm part of Windracers, as Noor said. We're an organization that wants to do freight transport using uncrewed aircraft systems. And today I'm going to be talking about the work that we're going to be doing in the Orkney Islands starting the end of the month, September 2021. So next slide, please. So just a little bit of background about Windracers, so how everything started. So the founders of Windracers in 2017 had this inspiration, and they looked at the problems that are in some places like South Sudan, where there are many people that require food rations and humanitarian relief items. And in the case of South Sudan, it is estimated that 7.5 million people are in the need of these items. Currently, the deliveries of these items are done either by road or by aircraft, but currently the civil war and the floodings have decreased the amount of aid that can be transported via road. So many of these items need to be transported via aircraft. So the founders of Windracers thought that this can be done with unmanned aircraft systems. So they went and contacted the University of Southampton. So the team on the right-hand side of the screen is the University of Southampton team, probably the leading university in the UK, working on unmanned aircraft system with in-house manufacturing capabilities like 3D printing, laser cutting, lots of CNC machining, and a lot of experience both developing and operating UAVs. That including the first twin engine that had an authorization to fly in the UK in 2012. So next slide, please. So during the last decade, there has been a lot of talk about the benefits of using UAS on crewed aircraft systems due to the cost and things like that. But basically, we know that for this type of mission, the amount of automation that can be applied to these systems can be very beneficial and reduce the cost of this type of missions. For widespread distribution and the high throughput that can be gotten from automation. Next slide, please. So this is about the conceptual design. Basically, the initial requirements that the University of Southampton had for designing and developing this aircraft was 1,000 kilometers of range, carrying 100 kilograms payload, a lot of focus on the reliability of the aircraft and redundancy of the critical flight systems, that's something that is easy to maintain and that has small ground footprint. And most importantly, being able to operate in really rough areas and operation from short and prepared runways, just preparing this to operate in places like Africa. Next slide, please. So these are the specifications for Ultra TD2. So it's TD2 because this is the second generation aircraft. First generation aircraft, Ultra TD1, flew for the first time in summer 2019. And from then on, we have been doing a lot of improvements. This is a narrower body and improved performance aircraft. So the aircraft that you see there is Ultra TD2, has a wingspan of 9.7 meters. So for reference, this is pretty much the size of a small manned aircraft like a Cessna 172 or a C-42 aircraft. It has an empty weight of 285 kilos and a maximum takeoff weight of 400 kilograms, out of which 100 kilograms can be payload. Current fuel capacity is 33 liters and flies with about 9.5 liters per hour. So about 3 to 4 hours endurance is what we currently have. And we're moving on to the next iteration, which will have between 6 and 7 hours endurance. The usable volume, and that this is something that is probably sometimes more important than the payload mass, is 700 liters. That, to give you a reference, is as big as the boot of a SATE car. It cruises at about 75 knots, and its wind limitations is 40 knots total wind and 20 knot crosswind for takeoff and landing. Next slide, please. So I talked about the reliability and about the redundancy of the systems of Ultra UAS. So when we came up with this design, we decided to basically discretize all the control surfaces so that we can have multiple reliability of or multiple redundancy of these flight critical systems. That means that if a section of an aileron fails or is broken, then the flight can continue without affecting the safety, because the other sections will take over. So we have multiple redundancy of all flight critical systems like engines and flight control units. So in the flight control unit, we use the distributed avionics masterless flight control system. This is just very different to the philosophy of current flight controllers in both civilian and military uncrewed aircraft. So usually when in systems there are like two autopilots, there's usually a system that is called the arbiter, and this arbiter makes decisions on whether one autopilot is has failed or not. In this case, what we have is 3 flight controllers with lots of sensors and actuate nodes that are available to them within a network. So there is no single point of failure, and even if 1 or 2 flight controllers fail, the aircraft can continue flying safely to its destination. Other features of the systems over the internet control, that means that the operator doesn't need to be co-located with the system. It can be controlled from anywhere in the world. It has an in-house designed health monitoring system that tells the operator on the ground everything about what's happening with the engines, electric system, and fuel system, and basically the overall health of the whole aircraft. And the aircraft is pretty much weatherproof. All the electronics are enclosed in IP-rated boxes, so the aircraft can fly in rain, and as I said before, in high-speed winds up to 40 knots. Next slide, please. Okay, so a little bit of the work today. So as I told you, TD1, the first generation of the aircraft, flew in 2019. And then at the beginning of 2021, we started flying TD2. However, we've been doing several operations, and here I'm just showing a few of those that we have done. So during the first lockdown, because of COVID-19, we did the first point-to-point VV-loss operation that has been done by a civilian UAV here in the UK. This was a relatively short flight between a location called Leon Solent and Binstead in the Isle of Wight, just about 12 kilometers long, but it was a big milestone for this type of operations. As you can see in the top left picture, there's a person loading the aircraft with these containers that had NHS equipment and just samples. And in the bottom right, you see the picture of the route between both points. So we were carrying in an average of 40 kilograms, 700 liters of volume. And again, this was a world first that was documented everywhere. And there are lots of videos and footage that can be seen online. Next slide, please. So later that year, so in December, we did the first flight to Isles of Scilly, from Land's End to Isles of Scilly, also carrying NHS support. It was an average load of 50 kilograms. This is about a 23 nautical mile route between those 2 points, about 50 kilometers. And it was done in less than an hour return flight. It was a little bit constrained because of like the air traffic in the area, so we had a really short time frame to this flight, but it was complete then in December last year. Next slide, please. So we continued working in the Isles of Scilly this year. We used the second generation aircraft, so Ultra TD2 is that one in the picture. So we had scheduled flights for 4 weeks. Basically over a 1 month, we had scheduled flights from Perranporth to the Isles of Scilly to St. Mary's. The top left picture is the trace of the aircraft based on the transponder signals, and the bottom down picture is us carrying the Royal Mail Yorks between Perranporth and the Isles of Scilly. So it was a total of 211 kilometers flight each day, return flights between Perranporth and the Isles of Scilly. We were carrying both post and medical supplies This was also a very constrained flight due to the schedule and due to air traffic, but it was very successful. We had a lot of not great weather. We had also 40 knot winds, and then basically we proved the robustness of the system. Next slide, please. So now I want to tell you about what we want to do in Orkney. This is within the framework of the project SATE. So we will be doing operations between the Orkneys, the Shetlands, and mainland Scotland, but mainly based at Kirkwall Airport. So to begin with, the beginning of this year, we started looking at use cases. So we've been talking again to Royal Mail, to the NHS, to industry around the Orkneys and the Shetlands, and looking at what is the interest of using this technology to having transport to isolated areas and to some islands that don't have as much logistic support at the moment. So we would like to have postal and medical logistics from main towns to remote islands. So we'll be flying from Kirkwall to Wick. We will be flying to North Ronaldsay, Fair Isle, and then that will happen during autumn this year. And then next year, in March, we will start also some routes between Kirkwall and Lerwick, and finally to Unst, which is the most northerly isle of the UK. So we will try to overcome ferry and commercial airline scales and COVID-19 restrictions. We can fly in lots of weather conditions. So sometimes if weather is restricting flights, we can still fly. We will be doing long-range autonomous BVLOS flights. And again, the longest flight will be probably from Kirkwall to Unst, which is about 250 miles. Next slide, please. So this couldn't have happened with all the help with all the air traffic controllers and air traffic service units. So the way we're going to be doing this is using segregated airspace. So for those who don't know, this is temporary danger areas or temporary corridors where only the UAVs will be flying between those 2 points. This is due to currently that we don't have a certified detect and avoid system. So the segregated pieces of airspace will enable us to fly from point to point without having other traffic, having incursion of other traffic into this airspace. So in order to set up these pieces of airspace, we've done lots of engagement with local and national stakeholders, and we have organized this schedule of flights that doesn't overlay with other flights of Loganair and other companies that fly in the area. Next slide, please. So basically, what we will see during the SATE operations of Windracers, initial phase starting 27th September and running up to the 24th of October. We will be doing routes between Kirkwall and Wick, Kirkwall and Ronaldsay, and Kirkwall and Fair Isle. And then the second phase of the project, starting March next year, will cover between Kirkwall to Lerwick and then to Unst. Flights can be followed using Flight Radar 24. The aircraft is equipped with electronic conspicuity, so usually it shows up in Flight Radar 24. Next slide, please. So finally, just talking a little bit about the development pipeline. So we have Ultra TD2. We have done lots of improvement into the performance of the system, but we have been working on 5 different lines of development, which are automation, communication, performance regulation, and data. So first, in the automation, we will be able to accommodate to environment and system status. So right now we have this human controller that is looking at all the health of the systems and making decisions and navigating and changing parameters of the system at all times. So we will reduce that human intervention by using data from the health monitoring system to make decisions and to accommodate to the environment. That way, the operator doesn't need to have so much input during the flight. We're also working on communication systems. So in November, we will release beyond radio line of sight command and control system. So we'll be using multiple channels of communication, serial line of sight radios, 4G and satellite communications. We are also working on performance to increase the payload and range. The next generation of the aircraft will have wet wings, so we'll have probably 3 times the fuel capacity that we currently have. And we have a team that is working on alternative modes of propulsion, so checking how we can convert these aircraft either on an electric or hydrogen powered system. And we're also looking at a heavy fuel engine, mainly for maritime operations, but concentrated on alternative and sustainable modes of propulsion. On the regulation part, something that probably all UAVs or uncrewed aircraft companies are looking for, and is beyond visual line of sight operation in unsegregated airspace, and not having to use this sort of temporary danger areas. So in order to do that, we are working on several projects, including something called Class Lima, which is based on electronic conspicuity. And when I talk about electronic conspicuity, for those who don't know, is things like transponders. So it's an electronic system that sends signals telling like, hey, this is this aircraft, this is where we are. So based on those radio signals, we can provide separation and collision avoidance between the UAV and other aircraft. And then finally, we're working on data. So uncrewed systems are usually very data rich. So all the automatic flight systems, they collect data, they log data. The computers that are used to control them, they log data. So we are gonna exploit data in support of flight and maintenance operations via APIs. That means just automating all the life of the aircraft, both in flight and when it's on ground. I think that's basically it, what I wanted to tell you today. So back to you, Noor.
Thank you, Herman. So the final 2 speakers are my colleagues at EMEC. And Dr. James Walker is the Hydrogen Development Manager at EMEC, where he seeks out the opportunities in research as well as business opportunities and takes them forward. And before joining EMEC, he worked for the Carbon Trust, carrying out research in low carbon energy systems. Then with him is also Jerry Gibson, who's a marine engineer working as an operation technician at EMEC and involved in all the hydrogen projects, and particularly the maritime ones. So the screen is yours, James and Jerry.
Thanks very much, Noor. Much appreciate the introduction there and the invitation to speak this evening, and glad to see Jerry's made it along. It was a bit touch and go there for a while, but yeah, very, very pleased to be with you all this evening. So we're going to talk through a little bit around EMEC's work in looking at transport sectors. So we're relatively well known now for our work in hydrogen, but we're becoming increasingly involved in looking at how that hydrogen can be used to reduce some of the greenhouse gas impacts of the transport sectors, particularly in Orkney. And hopefully that's going to be of interest to you and very relevant to tonight's proceedings. So that's the premise. Next slide, please. Next slide, please. Yep, thank you. So I'll just very briefly introduce EMEC and what we do. So we are best known as a marine energy test and demonstration centre, where we have 2 facilities, one off ED and one down at Billy and Crew, where we test both tidal and wave devices. And as a result of the energy system context in Orkney, whereby it's really difficult to increase capacity for exporting power, we started to look at hydrogen a few years ago. So I'll come onto this in a bit more detail, but essentially we, with some partners, deployed an electrolyzer and made some hydrogen, and then really needed to work out what on earth we were going to do with that. So that's really where the rest of our work has come into play, and that's what the other images show, and that's the focus for the talk this evening. So next slide, please. I won't dwell on this one, but this is just a holding slide, I suppose, to make clear that everything that we do at EMEC is motivated by the transition towards a net zero economy or energy system. So all of our work is looking at reducing time, cost and risk that is associated with new energy technologies, which can hopefully contribute to a cleaner future. And we do this through a living lab process. So we try to undertake research in the real world and work out what happens when you move something from say a university lab out to a real world context, understanding the health and safety impacts, the regulatory impacts, the practical aspects, thinking about how different technologies will interact in real world systems. Next slide, please. And one of those aspects that we're focused on, of course, as I've already mentioned, is hydrogen. And there's a good, I think, rationale as to why. What you see on the left-hand side is a visualization of some of the energy system dynamics at play in Orkney. So on the left, you see energy demand in Orkney, or power demand, sorry, and you see that's quite a bit lower than the power that we can possibly produce from renewable sources on the right-hand side. It's a well-known fact that Orkney produces well over and above its possible energy demand in terms of renewable power. And hydrogen is considered to be one way of possibly storing some of that power. So the premise is you have excess renewable electricity, you use that to make hydrogen, and then you have that store of fuel or energy that you can use at a different time. And hydrogen is also particularly interesting because it can be used in a lot of different applications. So thinking about trying to transition the whole energy system over to cleaner varieties of energy consumption can be quite tricky when you think about some of the really difficult applications. So you see a few of these on the right-hand side. Some of these are more or less relevant in the Orkney context, but we tend to focus on the three at the bottom. So if you could please click once. Yeah, thank you. These are the ones that we tend to think are most relevant in our Orkney context. So heavy duty transport is an obvious one because it's just quite difficult to replace fuels, fossil fuels or petrol, diesels, etc., with other alternatives. Batteries and electric or electrification will play a huge role in that for most transport applications. But thinking about big vessels, for example, in a maritime context or long distance aviation, where you need to think about how you'll possibly store the right amount of fuel, there's potential role for hydrogen essentially. So that's an area of focus for us. The other two aspects we won't touch on tonight, so I'll leave that for now. And on that note, next slide, please. Thank you. So this is just a quick overview of everything that EMEC is doing in terms of hydrogen, and really that is from source to use. So we are producing hydrogen on ED using tidal and wind power, both produced locally. We have a community wind turbine that we access there, and we also have our own power that we produce on our tidal test site, and we use that to power an electrolyzer. We then store the hydrogen that we produce. We load it onto or into tanks on board what are called tube trailers, specially designed for the roads on ED, which Jerry will talk about shortly. And we load those in the back of trucks. Load those in the back of the trucks, which then go on to ferries to bring them back over to Orkney mainland, where the hydrogen can be used for a whole host of things, which I'm going to talk about in more detail. So next slide, please. And just to further that introduction to some extent, I like to talk about what I am starting to see as the Orkney hydrogen economy. So as we develop more and more projects and as other organisations become more and more interested in the role for hydrogen in the Orkney energy system, we are seeing the development of what could hopefully in the future be realistically described as the hydrogen economy, whereby hydrogen produced in Orkney can be used to meet energy demand in Orkney. So you have this future history, as it may be, where fuel that's produced in Orkney can actually address the needs of transport demand in Orkney without having to import fuels. And I think that would be really transformative in terms of community resilience. So that's all I wanted to say on this one, other than just to highlight the two projects there that we're heavily involved in, led by other organisations though, so worth referencing the key role that many of the partners that we work with locally play in the work that we do. Next slide, please. Thank you. And next again one. So I'm just going to talk through some of the projects that we're involved in a maritime and also an aviation context. So we won't spend much time on the aviation aspects. That's been well covered in terms of the two talks we've heard already, but we're also involved in this area. So as I mentioned, it's potentially a good use of hydrogen, potentially an important role for hydrogen in the future. And that's gotten us involved in a couple of projects looking at different applications there. So the High Flyer 1 and 2 projects are ones that have seen the conversion or the retrofit of existing aircraft over to hydrogen fuel cell propelled propulsion. And our role in those projects is looking at refueling. So what you see here is a truck that EMEC commissioned and that we own and operate, which has an electrolyzer on the back to produce hydrogen, storage on board, and also a dispense capacity so that we can actually directly refuel an aircraft on airside. And that's quite an innovative bit of technology and really exciting bit of infrastructure for us to own and operate. And hopefully will be transferable in the future. Next slide, please. And then I'll just very briefly touch on this one. So this is the SATE projects that we mentioned a few times already. So this is run by Highlands and Islands Airport Limited, who own and operate Kirkwall Airport. And what they're looking to do is develop a sustainable aviation test environment. So looking at Kirkwall as a place that will be really ideal to test all sorts of aircraft. We've already heard about 2 of those so far. There are hydrogen elements there, so Loganair in particular are keenly interested in the role that hydrogen could play in their fleet. So we're playing a role there to support in using some of the refueling expertise that we have from prior activity to think about what it would look like to provide hydrogen to aircraft at Kirkwall Airport. So a lot of forward-looking thinking there. And next slide, please. Thank you. So I use this graph a lot or this picture a lot because I find it helps set the context up quite well. So I'm going to hand over to Jerry here, who's going to give us a run through of the maritime activity that we've been involved in and maritime ambitions that we have. But really, I just thought it was worth pointing out. I know this will not be news to anyone sitting in Orkney, but it's hard to discuss the energy system in Orkney without talking about maritime. So ferries are so essential to getting between the islands that really it's time for us to start thinking about how we make those cleaner and what the alternatives are. So over to you, Jerry. Thank you.
Thank you very much, James, and thanks everybody for having me here to speak. So the HyDIME project has been a really interesting learning process for everybody who's involved. What we're doing is retrofitting one of the auxiliary engines, which traditionally uses diesel all the time, with a hydrogen injection system. So we will be injecting hydrogen into the engine while it's going through its usual cycle. So that involves changing a manifold on the top to put a gas injector sort of next door to the fuel injector, the traditional fuel injector. And by doing that, we'll reduce the amount of sort of carbon fuels and so emissions as well. It says here on the slide that the project has faced these regulatory barriers, which is one of the biggest sort of stops that we've had in the project, if you like, because we have to go through a lot of processes and procedures and studies for people like Lloyd's Register and the MCA, who will ultimately give us the certification to be able to test this system out properly, and that's been, you know, quite a struggle to get through. But we've done not too badly, have we, James? I mean, we're getting there now, aren't we? With the next project coming up, hopefully we'll get by it. But before we got to the stage where we were doing the
HyDIME project, we had to use the, oh goodness, sorry, there's somebody at the door. James, can you, I'm really sorry.
No, that's fine. Yeah, sure, go ahead.
Sorry.
I think we'll go next slide, please. Thank you. So there's a couple of key aspects that we've learned through projects like HyDIME and some of the others that I've mentioned, and I'm just going to touch on these in detail. And the key focus points for these is looking at safety. So hydrogen is often regarded as potentially being more dangerous than other fuels, but the reality is that provided you know how to handle hydrogen and provided you put the right systems and practices in place, that's not the case. It's all about just learning a different way of working, essentially. And that's what we're going to touch on here. So next slide, please. Key one of these is technology. So looking at bits of equipment that are specially designed for using hydrogen, or ways of designing systems so that they operate together effectively to manage the use of hydrogen. So Jerry's the expert on this, so I'm going to stumble through this a little bit till she comes back. The key one here that I think is worth mentioning, Jerry, go on.
Hi, I'm really sorry. This has been a very strange evening so far. So anyway, the picture that you can see there is a multi-element gas container. So we use this to transport the hydrogen from the island of ED where we're making it to the mainland, and it's been specially designed to be light for the road. So we've got carbon wrapped aluminium cylinders on the inside, which are all piped together, and they're inside also, especially for the ferry travel, there is a sprinkler system as well for safety, and is all specially designed to be transported on the ferries. So it'll drive onto the boat, it'll get connected up to the boat's own fire system, so that if there was an emergency on board or a fire on board, you could keep the cylinders cool and safe. We also use these way quick connectors on the backs of the trailers for refueling purposes, so that there is a standard connection with all of our infrastructure in Orkney. So we've trained up, James touched on the training there, we've trained the drivers who drive our hydrogen around in the use of these quick connections at the sites and for the ferry as well. And we would hope to do the same if we're for the aviation side of things. So it doesn't matter where they go, everything is the same, and that is a good way to enhance safety in the system, so that you're repeating the same procedure no matter where you go. At the bottom here, we've got this innovation for storage below deck, and that refers to the storage that we have in the HyDIME project. It's called a TCS, and that's a tank containment space. And that was made especially for the Shapinsay ferry as like an innovative design to make sure that we're storing the hydrogen safely. So we go through these things called HAZIDs and HAZOPs, where we identify the dangers or possible safety failures there could be in a design. And the tank containment space basically keeps all of these cylinders inside another tank, and it has like a ventilation system that goes from one side of the ship to the other. So if there was ever a leak of the cylinders inside the boat, inside the tank, you could then turn the boat sort of broadside into the wind, and it would then naturally ventilate that system, and the hydrogen would just go out the other side, which I think is a really good design, and it's something that that the engineers did a very good job in designing, and it's totally new and it's not been done before. So next slide, please. So we touched on the training, and in Orkney, we, along with the Stromness Nav School and Orkney Ferries, we developed this hydrogen safety training for mariners, which is a tag on to the IGF code. The IGF training is training that mariners get when they're working with LPG or LNG gas. And we had to develop this safety training for hydrogen because LNG and LPG are a completely different type of gas that behaves very differently. So we basically have to sort of unteach some of the learnings that they learned at the IGF code for hydrogen. And it's the first time, as far as we know, it's the first in the world offering of this type of training, and it's been approved by the MCA. And you know, it's all local people to Orkney that are providing the training. And you can see in the pictures we've got the ferry, or some of the crew off of the Shapinsay ferry here, and along with one of the drivers from northwards, who's very good now and been through the training a few times. So it's very good to have him there helping as well. Can I have the next slide, please?
Back to me, just to close. Thank you, Jerry. Can we just get one more click, please, just for the final animation, gratuitous animation. So just in the interest of time, be very brief and just say, essentially, hopefully we've shown the role that hydrogen can play in some of the different transport elements, looking at the Orkney energy system and the future Orkney hydrogen economy. So building on the point I was making there about the vessels that you see in the picture here showing an inherently maritime orientated environment, we've also got the aircraft. So there's plenty of opportunity in the future for hydrogen fueled aviation in Orkney. So I know there's ambition to consider the inter-island routes, and we would obviously very much welcome that and look forward to working with partners to see what that looks like in the future. So that's us. Thank you very much. Back to Noor.
Thank you, James and Jerry. So I'd like to invite everyone to turn on their cameras now, please. And then hopefully there is still a little bit of time for questions. Heather and Kathy? Sorry.
Yes, the questions have been flooding in, and we'll just go for some of the first ones. So I've got a question for Andrew to begin with. What proportion of an internal combustion engine power does the engine have?
So the electric motor has exactly the same power as the internal combustion engine it replaced, which is about the same as it is the same engine that's on the islanders that fly on the inter-island routes in Orkney.
Thank you for that. We'll move on to the next one. I've got a question from Eric, and he is asking, and I believe it's from the same talk, is the propeller and control thereof the same as for a combustion engine propelled plane?
Short answer is no. The longer answer is that, as you probably know, with an internal combustion engine, you run it at a fixed RPM to get the maximum power out of it, and you change the pitch of the propeller. With an electric motor, you have full torque right from so there's a flat torque curve for an electric motor. So one of the things we are investigating is how do you match a propeller to a constant torque but variable speed motor? So that's work in progress.
That's fascinating. Now we've got a question for Herman, which ties in a bit to what Andrew was speaking about. Are you considering using the electric motors for your unmanned planes?
Yes, so currently we have a team that are working on basically researching the market for the ideal motors for our aircraft. Again, that's a matter of working on sizing and finding the correct supply chain for it. It's not an easy task, but we're working on that. And one thing that many people ask is like, why didn't you just design it to begin with, like with electric motor or with something like that? And it's you cannot have too many layers of risk in the same system. So we need to test an airframe, that we need to test a flight control system. We need to have all the other support equipment that has a high reliability. And unfortunately, the engines that currently we know that we can use with high reliability that the regulator allows us to use is petrol engines. We know the operation of those. Once we have basically cleared and we are all happy with airframe flight control system, we can start introducing other types of propulsion that might increase the risk to begin with until we find that sweet point of low risk and good performance.
That's great. Let's move on to another question here. A question again for Herman here. Someone saying they're not convinced with the UAV petrol fuel based products. How much oil is used in production, or can you use bioplastics?
Yeah, I mean, currently, unfortunately, we like the engines that we use are petrol. The benefit is that the amount of petrol that we use compared to, say, other modes of transport and even to other aircraft. So if you compare it to like the smallest aircraft, crewed aircraft that is out there in the market, a Cessna 172, which is a single engine, those aircraft use above more than 30 liters per hour. Our aircraft, even though it's a twin engine, is using less than 10 liters per hour. And then if we compare it to say some systems that are used for emergency relief in the islands, like helicopters, like the AWS-139 that I was mentioning in one of the responses. Those are systems that use about 400 kilograms per hour. So even though we have two engines, the amount of petrol that we're consuming is low, and of course the carbon footprint is lower.
Fascinating stuff. We're coming towards the end of the session, so we'll have a couple more questions yet, and I'll just have a look. And right, I've got a question here for James and Jerry, asking from Mr. Rob Flett, what are the greatest risks and challenges when working with hydrogen that you're trying to overcome?
I think one of the biggest challenges, and certainly from a maritime perspective, if we're thinking about just the practicalities rather than the regulations, which has been our biggest challenge to date, would be how to get enough hydrogen as a fuel onto a boat, because it takes up rather a lot of space if it's not like very, very cool and under a lot of pressure, which then takes quite a lot of energy to get there. So it's how to get enough of it on board to do as much as you would do with diesel, for example. But there are ways that people are looking into that by possibly getting the hydrogen from another way, like ammonia or liquid organic hydrogen, or something like that. So that's a challenge. I don't know, what do you think, James?
I was just going to add slightly from a safety point of view. I was trying to make the point, and I always try to make the point, that it's not necessarily more or less safe. It's just all about how we handle it differently. But hydrogen is undeniably more explosive at certain ratios with other chemicals in the air or in a confined space, for example. And that's a challenge that we have to manage. We have the benefit, of course, that hydrogen is really buoyant. So because it's lighter than air, it can collect at the top of rooms, which is a danger, but also if you're in a well ventilated space, it can vent very, very easily. So that's both a challenge and a benefit in many ways, a property that we can use to our advantage. So I guess my lasting message there is always that it's not necessarily more or less safe, it's just that we need to really wrestle with how we work most safely with hydrogen. And that's what drives a lot of the work that we do, is understanding what that looks like operationally.
Oh, thank you so much. Fascinating stuff. I'm afraid we've just come towards the end of the session, so I'll have to close the questions. Thank you everybody watching on YouTube for asking those brilliant questions. I'm sorry we couldn't get to everybody. And that is the end of the questions. I think over to Noor.
Yes, that's me. Thank you, Heather. So I would like to thank all the speakers. So Andrew, Herman, James, and Jerry. Thank you all for your interesting talks and your input in this question session as well. And then finally, thank you, Heather and Kathy, and of course, the Orkney International Science Festival. Thank you very much for this session.
And thank you, Noor, for your excellent support in hosting the session today. It's been a pleasure having you. Just before we all go, I'd like to mention our next event at 9 o'clock, which will be a mix of music and stories. The music will be by 3 works by the Scottish composer Eddie Maguire, which have been influenced by astronomy. They're a bit special, with 2 of the works being performed by solo trumpet, and the third with a group of bass instruments, each one corresponding to a start in the constellation Aguirre.
It's beautiful music, and there will be stories as well of several folk who have lived in the Scottish borders with astronomy linking all their lives.
And at 9:30, we'll have the first session of the Festival Club, which you can chat with friends and hopefully some of our speakers from tonight as well. There'll be a direct link on the web and on the YouTube pages. But in the meantime, thank you everybody. Good evening and goodbye.
Goodbye.